Okay, math analysis. Here's problems 10 through 14 of the calculator, okay? So 10A, 10 has three different problems within it. These all are dealing with log stuff. Remember, if you have a variable in the exponent, usually an x in the exponent, you have to unwind this by using logarithm. It says use log or ln, which is natural log. It really doesn't matter what you use. For this one, I'll just go regular log. I've got something raised to the power, so this is the something raised to the power is isolated on one side. So I can just log both sides. Remember, when you log, the whole point of doing the log here is so I can take the exponent. So I can take the exponent and bring it around town. So that will come out in front. So this becomes 4x minus 1 log 3 equals log 28. Now it's just a matter of getting the x by itself. I can divide by log 3 on both sides. So you get some number there. And then again, just think, okay, now that 4x minus 1, that's all that's left over here. So I would then have to add the 1 over, so that goes away. And then you have 4x equals whatever this number is. Divide this mess, whatever all that mess is, divide by 4. And x is isolated. So x, I know it looks kind of nasty, but all I did was just move stuff away. You end up getting on this one 1.008276. And remember, you've got a calculator. You can check this actually. So, not even in your, go away, there we go. Not in your y plots. You could plot it, you could graph it, but I'm just going to do 3 raised to the, and put this all in a parenthesis, 4 times that answer for x, that answer I got for x, 1.008276 minus 1. And now again, I rounded this, but it should be real stinking close to 28. Okay, there we go. 28 with 4 zeros after it. That's pretty close. So there you go. So it does work. So you can check these. I'm not going to do it on all these, but you can check a lot of this stuff. Okay, so for 10b, you can't just log both sides because you have that 9 there. So I have to first divide by 9 so that it goes away. So I have e raised to the 3x equals, let's see, I could reduce this if I wanted to, or you could get a decimal, doesn't matter. Let's see, 3 goes in both of those, so 8/3. Now, you could use log, and that's fine, but if you remember, e and natural log are inverses of each other, excuse me. So they cancel each other out, essentially. So if I natural log both sides, bring this around town, just like normal log, bring that around town, you got the 3x out in front. The natural log of e, which would be here, the natural log of e is 1. And you could check that if you wanted on your calculator. The natural log of e, if I can remember where e is, there it is, second and above division. The natural log of e is just 1, so I don't really have to even write that. So natural log of e is 1, 3x equals natural log of 8/3, and then to get x by itself I just have to divide by 3. And you end up on that one with x to be about 0.326943. Again, that is rounded, but if you plug that into the original, 9 times e raised to the, in parentheses, 3 times that mess, It should get you really close to the number 24. There you go. There's your answer. 10C is a little bit different. We've already got logs in it. What you need to remember is one of the properties of logs is that if you're adding two logs, they have the same base, base 4, then I'm actually multiplying the stuff. So this and this are actually being multiplied together. So I can combine them. So I can say that this is the log, base 4, of, you could maybe put this in a bracket or whatever you want to do, x minus 6 times x. And multiply those together, equals 2. So then I can go ahead, I'm just going to distribute the x through. So this is really x squared minus 6x equals 2. Now, how the heck am I going to solve for x on this one? Well, what I'm going to do is do the actual loop. Remember, this really means in exponential, 4 squared equals that. So 4 squared equals x squared minus 6x. So x squared minus 6x equals, again, 4 squared, which is 16. This I can solve if I just move this over. X squared minus 6x minus 16 equals 0. Turns out this factors into a couple swoops. Numbers that multiply to negative 16 and add to negative 6, that would be negative 8 and positive 2. So I get x could equal 8 or x could equal negative 2. Now here's a huge alert. Let's go with figure. This will show up on the finals. You got to be careful. You have to check these in the original. You cannot take the log of a negative number. Log base 4, log base 10, log base e, which is natural log. No matter what, you cannot take the log of a negative number. You could try it in your calculator and you can see. If I did the log of negative 6, it's going to get mad at me. Nope, non-real answer. And really think about that. The reason that's not working is because you're saying 10 to some power equals a negative number. 10 to any power cannot possibly be negative. So, get back to our problem. You have to check these. So if I plugged 8 in here, you'd have the log of a positive number, 8 minus 6. If I plugged 8 in here, log of a positive number. You're okay. But if you do negative 2, you have the log of a negative number. Oops, that's not what we want. So that's out. So the only actual answer is x equals 8. And again, you could plug 8 into the original, and it should work. It's a little bit tricky in the calculator, but you can sort it out. Okay, now we're getting into the exciting trig stuff. Number 11, though, is a pretty easy problem. One positive and one negative angle, which are coterminal with that. Remember, coterminal simply means from wherever you're at, and actually it turns out that 3 pi over 8 is somewhere up here. It's not one of our normal ones, but that's not a big deal. Remember, coterminal just means if you add a full circle, you get to the same spot, or subtract a full circle. So you're adding or subtracting a full rotation, either way. In radians, that's adding or subtracting 2 pi. So just take 3 pi over 8, and I'm going to add 2 pi. Oops, but I don't want to add 2 pi that way. I got to get common denominators. So I'm actually adding 16 pi over 8. That's 2 pi. So I get 19 pi over 8. There's a positive angle that's coterminal. How the heck do I get a negative one? Well, I just minus 2 pi. So if I minus 2 pi, 3 minus 16 would be negative 13 pi over 8. And there you go. There's a positive and negative angle coterminal. Real easy. That should not be a tough one. Number 12 takes a little bit of work, but it's not terrible. It's just that it wants basically all your trig values. The sine, you've already got the cosine, tangent, the cosecant, secant, and cotangent. So it wants everything. all the trig values. Since, and on the directions it says figure out what quadrant you're in first. So there's a couple clues here. First thing is that the cosine of the angle, alpha, cosine's negative. All students take calculus. So if the cosine's negative, the triangle has to be over here somewhere. It's either up here or down here. Here cosine's positive, here cosine's positive. So it can't be there because cosine's negative. Now, sine of alpha is less than 0. That's a fancy way of saying that the sine is negative as well. Less than 0 is negative. So that's all that means. That's the only reason that's in there. So if the sine is also negative, that means it can't be up here. We've got to be down here. So now we know what quadrant we're in. So now we can just build ourselves a right triangle. And again, this is not a special right triangle. 2 over 5 is not going to be a special right triangle, but no big deal. Remember that cosine, think SOHCAHTOA, cosine means adjacent then hypotenuse. So from my reference angle, adjacent is 2, hypotenuse is 5. Find the missing piece of your triangle just by doing Pythag. 2 squared plus b squared equals 5 squared. So you get 25 over here. Subtract off the 4. So b squared equals 21. So b is root 21. Okay, so that's my opposite side. So now I can find everything I want. So the sine of alpha, remember that all students take calculus, sine is going to be negative, is negative, opposite over hypotenuse. Root 21 over 5. I'm just going to write the cosine just so I have these things in nice order. The cosine it gave us was negative 2/5. The tangent is opposite over adjacent, but tangent's positive. So root 21 over 2. Now it wants the cosecant of alpha, the secant of alpha, and the cotangent of alpha. How the heck do you get these? Well, remember, they're just reciprocals. So all you do is flip the fraction. So, at least for the cosecant, if I just flip the fraction, I'd have still a negative, definitely. 5 over root 21, just doing a little side work here. And, oh wait, we don't like having a radical down there, so you could clean that up. You end up with 5 root 21 over 21. Again, all I did was flip that, and then I rationalized it. By the same logic, flip this. That's a real easy one, obviously. Negative 5 halves. Flip this, and again, you're going to end up with, if you flip this, I'll go another color for the cotangent. If you flip this, you'd have 2 over root 21. If you rationalize it, you get 2 root 21 over 21. And there's all your values. Only the tangent and cotangent are positive because we're in the t quadrant. So again, the first thing was using that fact that that was negative and that the sine was negative to figure out that I had to be in this quadrant. And then I just drew the triangle, figured out my missing side, and just started doing all the trig. So that's every value there. On number 13, it asks for the amplitude, the period, the phase shift, and the vertical shift. All the interesting stuff we can have. Remember, the amp and the vertical shift are the easiest. So phase shift. Actually, let's do period next. Phase shift and vertical shift. The amp, be careful. Remember, the amp, this means it's reflected, but amp is always positive. So the amp is just a 6. So that's easy. The vertical shift is down 2. So you could either write it as down 2, or you could say negative 2, whatever. Either one. The period and the phase shift are the trickier ones. That deals with the stuff that's here. Now, if you remember, get that highlighted. So we're looking at that stuff. If you remember, we have to factor this out. All the rules that we have assume that this has been factored, so it's moved right here. So this, so the rest of it, -6, we don't really care about. Sine, here's what we care about. If I factor out the 4, I'd have x plus pi over 4. And then I still have the -2 at the end. Okay, so I'm just really looking at the blue stuff here for the period and the phase shift. So, and you can check this. That would be 4 times x, 4 times pi over 4, so the 4s would cancel. You'd be left with pi, which is what we had. Now you can extract the phase shift real easy. Phase shift is just a horizontal movement. Plus pi over 4 means actually we are moving to the left pi over 4. Remember, plus inside that in the parentheses actually means go the opposite way. Or you could say the phase shift pi over 4. And remember, this is not the period. We had to do this. And again, this should hopefully bring back exciting, fond memories from January. But what's the normal period of sine? Normal period of a sine machine is 2 pi. We divide that by that. So 2 pi over 4, pi over 2. And there's all our information that we wanted. On the last one here, it only wants, for part A, 14A, the period and the phase shift. So again, we've got to factor out, oops. So looking at this, we've got to factor out whatever's hooked onto the x, which is the 3/2 in this case. Okay, that's a lot trickier, but we can do it. So again, I'm not really going to worry about the rest of this stuff. Here's what I care about. Factor out the 3/2. I have x minus, what times 3/2 gives me pi over 4. That's kind of nasty. I mean, you could guess and check, but you could also just do it this way. It's saying 3/2 times what? Happy face. 3/2 times something has to equal pi over 4. So times by 2/3, times by 2/3. So whatever that what is, well, this you can solve. So we've got, reduce, excuse me. 1 there, 2 there, you get pi over 6. I would definitely pi over 6. I would definitely check that. Obviously 3/2 x. If I multiply 3/2 times pi over 6, just kind of an aside here. 3/2 times pi over 6. So you'd have 3 pi over 12, which that does equal pi over 4. So we're good. So again, you have to factor that. Now the phase shift is easy. Again, it wants the period and the phase shift. Now that I've factored it, the phase shift is just that. So x minus pi over 6 means move to the right pi over 6. Or you could say positive pi over 6, or just pi over 6, or something. Either one. Now remember, this is not the period. You say, oh, what's the normal period of a cosine? Normal period of a cosine is 2 pi. It's a pi symbol. And I divide that by this number, just like on the previous one. I took the normal period of sine and divided by 4, divided by the number that I factored out. 2 pi divided by 3/2. So I can multiply by the reciprocal. So I end up with, oh darn, nothing cancels really. But I end up with, oops, scratch that. 4 pi over, let's try that again. 4 pi over 3. There we go. That's my period of the function. So not a very pretty one, obviously. You think maybe you'll have one that's not so pretty on the test? Yeah, probably. So there's the period and the phase shift, 14a. Now 14b says how many complete cycles would it complete? Yeah, that seems like I'm doing a little bit too much repeating there. But how many complete cycles does it complete over the interval 0 to 16 pi? Remember, the period, 4 pi over 3, so let me bring that over. So the period, again, was 4 pi over 3. That's how long it takes to complete one cosine cycle. That's a cosine cycle. I want to know how many of those happen in 16 pi. Well, 0 to 16 pi, I want to know how many times that goes into this. In math, we call that division. I want to know how many times the period goes into this entire length. Like if I was looking at the x and y axis, and here's 16 pi, obviously here's 0. I'm wanting to know how many of those, how many of those happen in this interval, though I just divided into it. So again, just like before, multiply by the reciprocal, so this is really 16 pi, I don't know why I wrote over 1, but anyway, 16 pi times 3 over 4 pi. Again, all I did was flip the bottom. Let's see, pi's cancel. 4 goes into 16 4 times. So 4 times 3, 12. That's how many cycles. So I'd have 12 cosine waves, top to top, in between there. Actually, I think those started, that actually would have started low, but whatever, because it was a negative. But that doesn't influence the cycle, so 12 cycles total. All right, so that puts us well over halfway through the calculator OK part.